Hi there, this is Math 116 and this is section 3.1. So we're taking a break from parabolas and moving on to matrices. So matrices is the plural of a matrix. Matrix is one thing. The matrix is one thing. Matrices are many things. So matrices are a way to organize a bunch of data into these square or rectangular patterns so that we can organize and use big data. And as you all know, big data is very hot and sexy right now. All the books are talking about it. So a matrix looks like this. If we have some matrix A, we use these sort of square brackets here, and we have entries. They're like blank spots. So we would say like 4, 5, 6, 7, 8, 9. So each blank spot is an entry like this. So this whole section, section 3.1, is just talking about the basic elements and things that you can do with a matrix. So the first thing to keep in mind with a matrix is that matrices have dimensions. So the dimensions of the matrix are the number of rows and the number of columns. And they are almost always, every book I've seen, you start with rows first and then you go by column. So it's row by column. And I remember it because it's RC. Now your book uses this notation. They let M be the number of rows and N is the number of columns. So if you have a matrix that looks like this, if you say A is 3 by 2, that's a 3, then that tells you that you have 3 rows like this. 1, 2, 3. They weren't evenly spaced, sorry, and 2 columns. So there's the first column, this is the second column. So our matrix looks like this, but instead of dots, there would be numbers. Okay, if you had a matrix B that was 2 by 3, you can see this pattern, can't you? All right, there's 2 rows, 1, 2, because that's the number of rows, and 3 columns. So that was the first column, it's the second column, here's the third column. So 3 by 2 is different from being 2 by 3. So the first thing I want you to know is that matrices have dimensions and it's rows by columns. And each one of these entries here, one of these little numbers that goes into this slot, we call those entries. You can imagine if you were a bookkeeper and there was a blank space there, like in an Excel program, then you would call those entries. Okay. So another thing to keep in mind is the zero matrix. When we talk about the zero matrix, we are talking about a matrix that is all zeros. So every entry is 0. That's somewhat intuitive, perhaps. So if you had a zero matrix, I don't know if they use the Z, I would use a Z, but if it was 2 by 3, right, zero matrix, that would mean you have 2 rows and 3 columns. There's 2 columns like that, and every entry is 0 like this. Now there are different, you can have different dimensions of the zero matrix, but the thing to keep in mind about the zero matrix is every entry is 0, which again is fairly intuitive. These look like dice to me, but they're not dice. They are zero matrices. The other thing, I say the other thing, there's lots of things to keep in mind here, is you can transpose a matrix. Transpose. Transpose is a fancy word for flip. Probably in 200 years they'll call this matrix flipping. But if you, here's the notation, is A with a T. T stands for transpose. And we're essentially going to flip the rows and columns. So you're going to change places. Rows and columns are going to change places. To me it seems like a square dance. They're all just going to shift around and change places. So if A is the matrix that looks like this, 1, 2, 3, 4, 5, 6. Again, these are separate entries. It's not 123. It's 1, and then 2, and then 3. This is a 2 by 3 matrix, rows by columns. A transpose is going to look like this. Every row becomes a column. So now it's 1, 2, 3, because this first row, this thing, turns into a column. Right? 1, 2, 3. The second row turns into the second column. 4, 5, 6. And you will notice the dimensions of the transpose matrix are 1, 2, 3, 3 rows by 1, 2 columns. So the dimensions flipped. It went from 2 by 3 to 3 by 2. See, it flipped. They flipped. Transpose. All right, so let's review what we have. This one. So far, we have matrices are these rectangular arrays of numbers. They have dimensions. It's row by columns, and they have entries. That's what we've done so far. Second page, we have the zero matrix, and we can transpose a matrix by flipping the rows and columns. Okay, third page, we can add and subtract matrices, but they have to be of the same dimension. Subtract. We can add and subtract matrices if they have the same dimensions. You can only add and subtract matrices that have the same dimension. And you do this by adding or subtracting the elements of the matrix. Elements. And when you see how to add and subtract it, the same dimension thing is going to become clear. So suppose you have A is a matrix that is 1, 2, 3, 4, 5, 6, and that's 2 by 3, right? 2 by 3. And B is a matrix. Let's go 1, 1, 1, 2, 2, 2. Huh? How do I think of these things? This is also 2 rows by 1, 2, 3 columns. Ta-da! All right, I haven't done anything yet. I just listed the matrices. If we want to add the matrices, we have A plus B. That's what it looks like. You just write A plus B. Let's say this is our production for 1 year and production from another year, and we want to find the total production. So you can just add the entries of the matrix. So you add each one. 1 plus 1, that's 2. 2 plus 1 is 3. 3 plus 1 is 4. You're adding each of the ones that are in the same position. 4 plus 2 is 6. 5 plus 2 is 7. Go to this last place. 6 plus 2 is 8. So it looks like that. And you'll notice the A plus B matrix is still 2 by 3, because it's 2 rows by 3 columns. Now we can only add them because there's one, they match up. So imagine if I could physically pick up this B matrix and move it and stick it on top of the A matrix and then add them in a 2-dimensional or 3-dimensional way. That would be cool. Can't do that on this little computer, but this is how we're doing it. You can do the same thing. I'll use blue, if we can see the blue. A minus B, you can subtract the matrices by subtracting the elements. So I'd take 1 minus 1 is 0, 2 minus 1 is 1. I'm subtracting the elements that are in the same position. 3 minus 1 is 2. Down here I'd be at 4 minus 2, that's 2. 5 minus 2 is 3. 6 minus 2, see I'm taking this position, minus this position is 4. And the order matters. It would be different if I was doing B minus A. So here's the matrix that is the subtraction matrix, and you'll notice it is still 2 by 3. The dimensions have stayed the same. And suppose your matrices are not the same dimension, and they say find A minus B, and A is 2 by 3, and B is 4 by 6. How do you answer that problem? You say, not possible. If you tried to do that, a big sinkhole would open up in your house. I'm kidding, you just can't do it. So you can only add matrices that are the same dimensions. So there's another thing to keep in mind. And this is the, what do they call it? The negative matrix. The negative matrix. So if I said, here's 1, what's the negative of 1? You'd say, well, that's negative 1. So if we have a matrix A that's equal to, guess what? Yeah, are you thinking 1, 2, 3, 4, 5, 6? That's what I'm thinking. Okay. But now I'm going to shake it up on you. I'm going to go 1, negative 2, negative 4, negative 6. If we want to say what is the negative of this matrix, so the negative of the matrix A, you take the negative of each entry. So you just look at every single entry and make it negative. So it's negative 1 there. So multiply this, essentially changing the sign. So negative 1 times negative 2 is 2. Change the sign of 3, negative 3, 4. Negative 4 becomes positive 4. Negative 5. And the negative of negative 6 is positive 6. You're essentially changing the sign of each entry. change the sign. All right, so there's another thing we can talk about, and that is scalar multiplication. I think each one of these concepts is fairly straightforward, but there's so many little concepts that might become a bit confusing. So we're just taking them one at a time. When the book talks about scalar multiplication, they're talking about doing a scale factor, which would be an excellent name for a reality show, scale factor. Or they're talking about multiplying by a constant. Sure, we can do that. So suppose you wanted to say, I want my matrix. I'm going to shake it up again and go 1, -2, 3, -4, -5, and 6. I'm so crazy, and I'm just going to take that multiplied by 3. -3. Sure. So now, suppose you were trying to scale this. This is all your production, and now you're cutting back by a -3 number. You're cutting back on production a lot or whatever. So the way you do this is you multiply each entry by -3. By the scale factor. Scale factor. Next on Fox. Okay. So in this case, 1 times -3 is -3. -2 times -3 is 6. Huh? Sign change. 3 times -3, -9. -4 times -3 is 12. -5 times -3, 15. -3 times 6 is -18. So these problems are not so challenging per se in the math, but working with the numbers can be a bit new and confusing for some people. And there's one last type of problem I want to show you from this section so that you can feel excited and prepared to do them. Question number 31 gives you a matrix that looks like this. X, 3, and then 2x minus 1. Notice these are all separate entries. And then you have y, 4, 4y. Okay, so this matrix is, what are the dimensions? 2 by 3. 2 rows, 3 columns. This equals another matrix that is 2x minus 4, z, as in z, 7, 1, w plus 1, and 3y plus 1. All right. So these are two matrices that contain variables, and the question asks you, get away from there, wx, they say find wx, y, and z. Okay, and we're going to do this because we know that if two matrices are equal to each other, that means the entries are equal to each other. So the first thing we know, because of these two, is we know that 2x minus 4 equals x. So if you subtract an x from this side, you know that x equals 4. All right, let's write that down. X equals 4. Check, got those guys. Let's move to this entry. Oh, that one's easy. Z equals 3, right? Because they're in the same position, so they have to equal each other. 3. All right, 2x minus 1, I'm moving to this position, equals 7. We already did the x one, but I'll do it again just to make sure. 2x equals, bring the 1 over to this side, 8. X equals 4. Oh, we already did it. Now this position, y and 1. I like those. Y equals 1, because these have to be the same because they're the same matrix. Y equals 1. We have 4 equals w plus, w plus 1. So w equals 3. And finally 4y equals 3y plus 1. We already found y. We don't need to keep going. I know. Don't you want to keep going? Don't you want to check? Yeah, y equals 1. Same thing. So you didn't have to do a couple of these, but there they are. And that's how you do a problem like that. So quick review. Matrices have dimensions. It's rows by columns. The things inside are called elements. You can have the zero matrix, and you can transpose a matrix by flipping the rows and columns. You can add and subtract matrices, but only if they have the same dimensions. You can talk about a negative matrix where you change the sign of every entry. You can do scalar multiplication, and you can start a reality show called Scale Factor. And then you can do the scale multiplication by multiplying each element by whatever this constant is. And finally, if you have two matrices that are equal to each other and you have variables in the elements, then you can use the fact that the two matrices are equal to each other to find the variables. So that's essentially what you're doing in section 3.1. That's your quick round-the-world introduction to matrices. And then in section 3.3, you will see how exciting, I'm going to make this pen super big, section 3.3, you will see how genuinely exciting and useful these matrices are, which is why we're doing it. It was kind of a weird visual, but there you are.